Before you start watching, I should warn you that it may be hard to grasp some moments straight away, so I invite you to pause and ponder anytime you feel you need it. There are also text fragments in the following steps that provide the same content as the video. You may read through them instead of watching the videos if you find that format preferable. In Python, functions are first-class entities, which allows us to construct functions taking another functions as their arguments. Such functions operating on the other functions are usually called higher-order functions. It's a quite powerful tool for constructing more general solutions for some existing problems. A simple example is demonstrated in the first lesson of the course, where the toT function is defined. Here's another example. Suppose we use logs a lot in our program and would like to simplify the procedure of writing to a log file. It's okay to write the full open file name mode things and then use write and close methods explicitly each time we need. But if we're making it often and with a number of different files, we'd like everything to look more compact. We may define a function that takes a file name and returns a logger bound to that file name, which works very simple. We give a logger a message, it opens the file in a mode we need, appends the message to the end of the file and adds a new line character. Then closes the file. There is another way of using this functional feature which is very common in Python programs. Suppose we want to compare the time it takes to compute the 30 Fibonacci numbers by using the naive recursive approach and making it in an iterative way. Well, we could just print out the difference of the time function before and after executions of each of these two functions, like that. But that's some inferior copy-pasting. If some code is used more than once, it's good evidence there's something generalized there. That is totally the case. Instead of repeating the code over and over again, since we'd probably need to do something similar in the future, we could just design a function that takes some function as its input and returns a function that is essentially the same that was given, but it prints out the execution time before returning the value. The implementation could be something like that. I hope you are familiar with this star notation. When used with the function definition, these stars indicate that there could be an arbitrary number of arguments, and keyword arguments besides those that are written explicitly. So these star args mean that all the arguments given to the function after those explicitly specified in the brackets should be packed into a list named args. Star quarks means that all the keyword arguments given to the function, which are not among those written explicitly in the definition, should be packed into a dictionary called quarks. In this case, we don't know anything about the number of arguments that will be given to a function, whether they will be named or not, and what names they will have. So we just pack whatever arguments are passed into a list and a dictionary. When used outside of a function definition, these stars are used to unpack these structures. That means that by using func star args star quarks, we're calling the function passed as the argument of the timed with the arguments passed to the inner. This way, we pass some function to the timed function, and it returns a function that will do essentially the same thing we've done before. It will take whatever arguments you pass, apply the initial function to these arguments, and before returning the result, it will print out the execution time. So this timed function is kind of a wrapping around some other function that adds some additional functionality without changing what the original function actually does. Now, we can wrap this timer around our versions of fibs like this. As you can see, the new t functions behaving in exactly the same manner as before, but now we get an additional feature. Note that we could give a wrapped function not some other name, but to redefine the original function by writing fib equals time to fib. This pattern of redefining some function to be the same function wrapped into some wrapper function is a very common and useful thing. It's known as a decorator pattern. It's been used in Python so much it has its own piece of syntactic sugar. Suppose we want to make this introduce wrapper that takes a function and returns the same function that prints out its name before being executed. Now, instead of writing some func equals introduce of some func, we could write this add sign about the function's definition. It is equivalent to writing the definition first and then writing id equals introduce of id. If you see the syntax, just remember that this is the same as changing the defined function to the result of applying the function after the add sign to the defined function. Because the latter is perfectly understandable and the former may seem to be some kind of voodoo witchcraft when you see it for the first time. As you can see, it is a very neat feature of extending the functionality without actually digging into implementation. This approach is used a lot in functional programming, and using decorators is a nice tool to achieve that. Let's look at another example of using decorators. Recall how slow is the recursive implementation of fib due to nonlinear recursive scheme of computation. This problem could be solved though. You would have a wait for a function to remember its result on some particular inputs. Thus, before computing the result, we could check whether or not the answer is already known to us, and we can just return it straight away. This trade-off between memory and the speed of computation is a quite common thing to occur, and since we're trying to preserve the purity of our functions, we may be sure most of the time that the output of our function should be the same as long as the input doesn't change. Thus, implementing such a feature would let us to make even more advantages out of using functional approach. So we want to have some way of adding an arbitrary function, a cache if you will. Adding some enhancing feature to an existing function is exactly what decorators are used for. Let's make such a decorator and test it. There are certain things related to hashing that you'd like to do with this implementation, but let's keep it simple for now. Everything is an object in Python, which we can make use of. Since functions are objects as well, we may define a new property for any function. Let's create a dictionary called cache for a function that is passed to the cache decorator function. Then, we will return this inner function that will make the same thing as the original func function, but before computing the result, it will look it up in the cache dictionary we've created as a property of the func function. If there is one already, the function will return it, otherwise it will compute the result and save it in cache. A rather straightforward implementation. As you may infer from the execution time, it actually helps. Decorators are awesome, but there are still some things left to discuss. Firstly, let's return to our ID function that is decorated with the introduce decorator. Suppose we'd like to print out the documentation or we want to receive its name manually. That's certainly not what we expected or wanted to see. It's kind of ironic that a function that introduces itself when called can't tell its proper name and what it does when asked explicitly. Of course, that's because the decorated function is not the initial one with some changes in its body, but this function inner that's using the original function as a tool for simulating its behavior. This can be fixed by manually setting the name and doc fields of the inner function to whatever they are in the original function before returning the inner. The problem is there is a lot of fields besides name and doc that you'd like to leave untouched in some cases, but manually setting all these fields is kind of lame and repetitive. So we wish to redefine inner so that it does the same thing it does, but there's a slight enhancement of it. That sounds like a job for a decorator. So we can generalize the solution of a problem of the decorator design with a decorator. Lucky for us, there is a solution in the functools module made for us. Functools, as one may infer from its name, is a module for working with functions, particularly higher order functions. There's this function called reps. Reps takes some function f as an input and returns a decorator. This decorator, being applied to any function, changes its properties like name, doc, and so on to those of function f. Thus, we may solve our problem by decorating the inner function with the decorator reps of func, because we want the inner function that we actually return when decorating the func function to have the same properties as this func function. As you may see, it works. I want to point out once more that it is not reps that is a decorator, but reps of func that is a decorator. It may be written in such a way because this @sign operator has a lower priority than the function application, but it looks like a decorator with a parameter. In a way it is, at least it is safe to think of it as a decorator with a parameter. What if we want a decorator with parameters too? Suppose we want to be able to specify the number of times that the function decorated with introduce should print out its name when called. How do we repeat this behavior of being in fact not a decorator itself, but a function that returns a decorator? Moreover, this behavior of the resulting decorator should depend on the arguments given to the decorator returning function. Well, quite literally we do exactly that. We just take our old decorator and add functionality that depends on some arguments that are not yet given. Then we add another layer. Instead of having a decorator function called introduce, we'll have a function called introduce that will seem to be a parameterized decorator, but instead it will take the arguments we wish to use and return the old introduce, which could now use these arguments. For the sake of clarity, the return function that is the actual decorator is called resulting decorator. Now we get the behavior we wanted. If we pass no arguments, there's still a default value of n equal to 1. The only problem is that we can't just omit the brackets since introduce itself is not a decorator anymore, but a function that returns a decorator. This works alright, but this number of nested layers makes it kind of unpleasant. I mean, we'll probably want to write such functions that seem to be a parameterized decorator in the future. So, do we keep this nested structure as a template and copy paste it each time? That's lame. It would be much more convenient if we could just list all the parameters we wish our decorator had after the func parameter. But the problem is this @sign syntax makes exactly so that @sign decorator before the def func is equal to writing func equals decorator of func after the definition of func. Let's solve a decorator designing problem with a decorator once again. This parameterized is a decorator that takes an initial decorator to make it a decorator with parameters. So it's decorating an initial decorator. Given an initial decorator, the parameterized function returns a deco function. This deco function takes the arguments we want to pass to the initial decorator as its parameters. Given these arguments, deco function returns the resulting decorator. The add sign operator is applied to this resulting decorator to pass it a function. Once the resulting decorator gets this function, it returns the result of applying the initial decorator to the sequence of arguments, where this function is the first one, followed by the initial decorator arguments previously passed to deco function. This result is well defined because the order of arguments is exactly the one from the definition we desired for our initial decorator with parameters to have. Now we can just define our decorator with parameters the way we want it to, and decorate it with the parameterized decorator. As you can see, it works. Let's try to go through the explanation once again.